Let's understand the forward kinematics. We have 25 minutes to cover all of these in, let's say, lesson. But after 4:30, as I heard, there is one more lesson for you. For that reason, we will be as quick as possible for the lesson. Forward kinematics. What was the forward kinematics? Do you remember? Yes?
We are calculating how would my end up if I move it in a specific diagram, in a specific movement.
Okay.
Or it may be the inverse, like if I want my hand to end up in that position, how should I do it?
Yeah. The difference is the input. And the forward kinematics, you use your joints and the rigid bodies, rigid parts of your body. And in inverse kinematics, you use the final point of that, let's say, part as input. Okay, that is the essential difference between the forward kinematics and inverse kinematics. The details are written in the lecture notes for the calculations, for the equations. You will continue with those. We will understand how can we calculate a possible movement of a, for example, arm, hand. We will learn how to calculate in this lesson. Bless you. When we come to the skeleton-based animation, the forward kinematics mainly focuses on the core mechanism of your skeleton. With respect to the animation, it allows characters to move fluidly. When we come to the pose computation, forward kinematics actually computes the position, orientation of limbs based on your joint parameters. For example, if I want my character to, for example, sit on a chair, I have to define the joint positions and the rigid body positions. Okay. What actually forward kinematics provides us? It provides motion playback. What is that? For example, for the character animation, if let's assume this classroom is a digital representation of, let's say, a realistic scene, let's say. In that realistic scene, if I want to, for example, playback a character for the forward kinematics, I only need to, let's say, store the possible input parameters of that character, not the whole motion. I only need the inputs. If I have the inputs, it means that I can playback that motion also, because I know the inputs at each time step and I know what will character make while it's moving. That is the simulation. Because in gaming world, you cannot actually store your, let's say, forward kinematic inputs. They may get the video capture of your game, of your playing. But when we come to the simulation, we have to actually store the input parameters of the character for the forward kinematics calculations. And also, forward kinematics provides the physics and control systems by modeling how characters react to external forces. For example, if I want to, for example, hit to that door, if I hit to that, let's say, glass, if that glass breaks, my arm will penetrate towards the outside. Forward kinematics provides these calculations. But when we come to the gaming, if you hit to the glass, it will not break. Or if you hit to the door, it will not break. If you do not define the, let's say, broken, let's say, state of that glass. And also you will not see the effect of, let's say, broke process of that glass. Because when you broke that glass, there will be still, let's say, forces on that glass. Because after the broken of that glass, the forces will not disappear. Okay? Articulated systems and kinematic chains. When we come to the kinematic chains, when we look at our skeleton, we have lots of joints and we have different kind of postures, movements, motions. But when we come to the forward kinematics, it calculates the possible motion of that rigid body part. Okay? And for the forward kinematics, you need to define the possible positions, position endings of the character. What do I mean? In the forward kinematics, my inputs are joints. My inputs are rigid bodies. My inputs are my actuators, which are our muscles. If actually calculate the forward kinematic with actuator, joint, and the rigid body, I can calculate the last position of my hand. Okay? That is the kinematics. X equals to V dot T. Okay? That's kinematics. When we come to the local and global space, for the local space, for the, let's say, posture and the, let's say, the when we look at the posture, if we do not define the postures, it will not be seen realistic as possible. For example, we can define the posture with let's say one local space and one local representation. We can also define the model with, for example, more than one local spaces. When we come to the global space, actually it computes the overall position and orientation of each point with respect to the posture. That is the difference. Yeah. When we come to the transformation in forward kinematics, first of all, we have to consider the joint transformations. Actually, it provides us the rotation and the translation of the character. Okay. For example, while moving my arm like this, I am actually making a swirl movement of my hand, but I am losing the joints of my arms, joints of my shoulders also. These transformation defines the parental joints. Parental joints with respect to the motion that I am doing or the character is doing. Okay? When we come to the homogeneous transformation matrices, in forward kinematics, it provides a smooth movement for the rotation and translation, and it creates an efficient chaining. For the swirl movement of my hand, I can make it like this. I can make it with my shoulders also. But if you define the transformation matrices with respect to the motion, the joints that you will calculate, differentiate, and the movement becomes realistic. And the other one is the chaining transformations. When we come to the global transform, it actually consists of parent transform and the local transform. What was local transform? Local transform was the movement of the rigid bodies. When we come to the parent transform, it actually represents the effects of that motion on other joints or on other local transforms. When we combine all of them, the motion occurs. For walking, I am using my foot, I am using my knees, I am using my legs, and also hips. I am controlling these parts of the body. What was the local transform while I am walking? Foot. What are the parental transforms? Hips, knees, and legs. Okay? When we come to the homogeneous transformation in matrices, when we look at the 3D space, we can pass from a motion to another motion in, for example, in a specific position of the 3D space. For example, I can start swirling of my hand from here, or I can start this motion from here. For example, it was on my shoulder, then I start my swirling. That increases the complexity, but it provides the homogeneous transformation from one motion to another motion. Okay? When we come to the forward kinematics algorithm overview, first of all, we should initiate the algorithm from the root joint of the skeleton. What are our root joints? Shoulders, hips, aren't they? Can I define with these joints like for example, a penguin walking? Yeah, that is the root joints. that you have to define. After that, you need to define the global transform of the other joints. I have to define the other joints, wrists, ankles, knees. Then I should create a matrix which represents the global transformation with respect to the motion that you are applying to the character. And also, you need to implement the child joints. What are the child joints? We learned the local parents, we learned the local transform, we learned the parent transform. What are the childs? For example, while I am...
are affected by the main joints.
What?
The child joints are the ones that are affected from the root joints.
Yes. And also, for example, while I am walking, am I walk like this? No. When we come to the child joints, my hands behave like this while I am walking. It keeps the posture of standing. But if I put my arm to the upper, can you see my fingers? Its posture differentiates. They are child joints. For example, if I drop my hand, as you see, my fingers move. But I am not moving my fingers consciously. You can try. Try. Just do not create any force on your fingers. Just like this. Then put your arm. Can you see the effects that your fingers moving?
It's like they go with gravity.
Yeah. And there's a force there on your child joints, on your child rigid bodies. The ground force. What was the kinematics? X equals v dot t, speed times speed cross times. When we come to the speed, what was the speed? Where's my pen? There. What is acceleration? For the vertical, it is g, which refers to the ground force. Okay? When we come to the recursive computation, for the joints, if we create an articulated system, it continues this process recursively. For example, while I am walking, I make walking for one step. It is similar with the next step. It's a recursive motion of your body. And I only gave my, let's say, character to walk command. I am not applying any kind of physics calculations for that motion. It makes one process, it calculates all of them, then it makes these motion recursively. Okay? When we come to the fourth kinematics, this algorithm operates deterministically and efficiently. What is determinism? What is stochasticism? What are those terminations? Determinism means if you calculate a motion any time, and if you calculate that motion, for example, 10 seconds later, with the same inputs, it should create same outputs, which refers to the determinism. If with the same inputs, my outputs differentiate, it's a stochastic way, and there is a stochasticism there. Okay? When we come to the degree of freedom for the role of joint parameters, we have to actually manage the complexity of the degree of freedom. Forward kinematics provides this process to us. For example, when we come to the joints, the typical rotation angles for joints, those are 1 to 3. But when we come to the possible translations contributing to a joint movement, the degree of freedom increases to 4 to 6. When we actually start to represent a system, the degree of freedom reaches to 10, which is which increases the expressiveness. What is expressiveness? Have you ever heard this? ON? Yeah. If we actually define our character with ON square, it will not be able to calculate that model in real time. For that reason, we have to keep our model at the complexity of n, not n square, not n log n as possible as creating the model. And the forward kinematics handles the computational complexity linearly. What is the linearity? Linearity are those equations. With the usage of these equations, you will be able to move your character. And the high degree of freedoms, the forward kinematics provides 100% efficiency because it is Newton physics. And one pose vector defined by a set of joint parameters. For example, standing still, one pose. Saluting, one pose. For example, sitting, one pose. And forward kinematics does not calculate any joint process in these poses. For that reason, we prefer to use forward kinematics. In forward kinematics, we need a motion, a movement. If there is no movement, we do not calculate any joints. When we come to the character animation pipelines, when we come to the keyframe animation, for example, animators define specific poses in some specific times of the, for example, the scene. Forward kinematics automatically calculates the intermediate poses based on those frames. What do I mean? For example, one pose is standing still like this. And if I want the second pose for the sitting, passing from standing to the sitting, forward kinematics calculates the motion. Okay? And also the motion capture playback, as I mentioned before. If you have the inputs and if you lock those inputs to anywhere, you can calculate your motion again. And also motion blending. When we come to the motion blending, for example, for the arm movement, do I actually move like this? No. There is a movement there with a smooth motion. With this forward kinematics calculation, you can blend the motion. You can create a smooth movement. And the forward kinematics relies on the physics, the Newton physics. For the real-time computation, if you keep your model with the ON performance, you can use your model in real time. What is the real time? What was the real time? Let's ask you. And you are software engineers too, you should be familiar with the real time. What is the real time, guys?
We get new data and compute it at the same time.
Not exactly. Real time means what?
24 frames.
Not only for frames.
Like real time, not seen out of. You said 20 to 60.
Yeah. Real time means if I want to represent a motion of a realistic motion of a human, I need to reach at least 24 frames per second, 24 hertz. It means in 1 second I need to calculate that model 24 times. That is real-time simulations. For example, for missile simulation, if it needs, for example, if it has a computer of 3 gigahertz, for example, it means that it needs 3 million calculations in 1 second. It means that I need to create, for real-time simulation, 3 gigahertz of simulation. Okay? What was the forward kinematics and the inverse kinematics? Inverse kinematics mainly depends on the target position. Forward kinematics mainly compute the input as a consist of joint angles, and the output is the resulting joint positions. Okay? When we come to the accumulated numerical errors, forward kinematics involves repeated matrix multiplications, which can lead to numerical inaccuracies. What does it mean? For example, we have matrices of motion of hand, we have matrices of motion of, let's say, arm, we have matrices of motion of, let's say, shoulder. But some of them actually cannot be applied with respect to the limits of the joints that I mentioned in the previous week. What was those? For example, if I put my hand like this, can I bring my fingers and touch to my palm? No. But if I keep my hand like this, I can touch to my palm. Okay? And also the precision loss in deep hierarchies. What is that? For example, if we have deep joints, what are those deep joints? When we come to the spinal we have joints, but those joints are inside of our body. Can we control our spinals? Can we move our spinals like moving of my finger? No, we cannot control the spinals. We can actually make the movement on spinals with the motion of the body. If I move like this, my spinals start to flex. Okay? But I cannot control my spinals while I am standing like this. Okay? Those are the deep joints. With respect to the hierarchical representation of the motion, they move. But it depends on the, how can I say, the representation of the deep joints. For example, for the bending, if I represent the bending of my body like this, if I do not make any movement on my spinals, it will not be realistic. If I move like this and if I move my spinals like this, the motion will be realistic. And the engineering practices for the stability, forward kinematics provides, actually mitigates the normalizing rotations of the transformation of the body. When we come to the joint transform computation, forward kinematics computes global transforms for each joint based on their local parameters. Skinning algorithm application, actually skinning algorithms use the computed joint transforms to deform the mesh. What was the skinning? It actually deforms the mesh. If I actually make any force on my, let's say, polygons on my surfaces, it creates these calculations. And the vertex transformation. Vertices are adjusted according to the joint movements, resulting in a deformed mesh. When we come to the real-time performance, forward kinematics are optimized for real-time operations in the animation and the simulation systems. Forward kinematics that we should actually we face for the mistakes and we should avoid incorrect joint hierarchy. While I am moving my hand, which joints will be calculated? We have to calculate, we have to know those. Then the local and global transforms that I mentioned, the wrong rotation order. Can I rotate my, for example, leg from here to there? No. Ignoring joint offsets, we have to consider the offsets of our joints. And the exploding skeletons, unstable motion, and the incorrect poses should be the common mistakes of forward kinematics. For that reason, we have different kind of approach solving these kind of mistakes. When we come to the key takeaways, forward kinematics computes pose from joint parameters. Skeletons are kinematic queries for our character. Transform chaining is our core mechanism. If we define the transformations into local transformations to the global transformations, it creates a chaining, transform chaining. And the forward kinematics is efficient and deterministic. When we come to the higher level of motion systems, which depends on the forward kinematics, it provides higher level of motion systems. In the next week, we will deal with the inverse kinematics. Forward kinematics was calculations of the joints, the inverse kinematics will depend on the last position that we request for that character. Okay. Last week we will mention on the inverse kinematics. Okay, guys.